So, hello everyone. I'm Yeet, and our respectable guest today is Greg Lowe, mostly known as the GDB guy because he presents a lot of talks about GDB and debugging uh, in the context of C++.
Thank you. Thank you for the intro,
yeah,
Yeet.
yeah, and I think Greg is going to talk about debugging complicated C++ applications because we all know that debugging is a very complicated task. It's very complicated. So like it's as important as writing a program in the first place. But yeah, we have a lot of tools like GDB, Valgrind, AddressSanitizer, and Greg is going to talk about them in detail, and he's going to inform us uh, in how to use them in how to use them effectively in production. So thank you very much, Greg, for joining our technical talk today as C++ community. We really appreciate your presence here. So yeah, do you need to add anything else?
That's it. Thank you for the excellent introduction. So I'm ready just to start the talk if you're ready for me.
Yeah, perfect.
So cool. Right. So let me just move some windows around. Okay.
All right.
And then I will just share my screen. Present, share screen. Here we go. I'm going to do the win. No, I want to do a screen. Do that one. Share. Share. Right.
All right.
There we go. So hopefully you can all see my presentation. If I hit that button.
Yes, we can see it. Yes, it's now in full screen.
Sorry?
Yeah, our talk is. Yes, perfect.
All right, we're live. I shall kick off.
I think I'll leave the stage for you, Greg.
Yeah, thank you very much. Thank you, Yeet, for the introduction. Thank you very much, everybody, for joining. And yeah, we're going to talk about debugging C++, C and C++ applications on Linux. Actually, a lot of this will translate nicely to other compiled languages, but we'll stick to C and C++ because they're kind of the main in all the demos and everything that we do. So let's start right at the beginning. Let's set some context, right? So this lady, Grace Hopper, you may know that she actually coined the term. She kind of invented the phrase debugging, or invented the phrase debug, right? Because when working on one of the early computers in the US, they found it didn't work. And when they actually figured out what was wrong, they found a moth in the relay circuit. And that's where the term bugs and debugging comes from. Actually, I'm going to guess you did know that. At least you thought you knew that. In fact, that is wrong. That is a little bit of incorrect history. I like to be pedantic, like all programmers, right? And so actually, if this is on the right-hand side here, this is the logbook. And you can see they say it's the first actual case of a bug, right? And so that kind of joke only works if bugs and debugging was kind of already a term. And in fact, it goes back to Edison in Edison's logbooks. There's talks of debugging. So the notion of bugging and debugging goes back a long way, but it really became synonymous with computers and software because there are just so many bugs in software, right? And this is a quote that I really like. You probably heard this quote before. It's quite a famous quote from Brian Kernighan. Brian Kernighan was the inventor of co-inventor of C and Unix and other things like that. So real kind of, grandfather of computer science. And he says that debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, then you are by definition not smart enough to debug it, right? And that's a kind of, it's a funny quote. It makes most people chuckle. And you realize quickly it's kind of true. And just like Yeet said at the beginning, it's kind of the hardest part, right? And I think what Kernighan was getting at here, what he really meant was keep it simple, right? Keep the code simple enough that you can actually debug it, You're not as smart as you think you are. But I think there's an interesting corollary from this. Another, if you play this through, an interesting implication of this statement, which is that debuggability is the limiting factor on how good we can make our software, right? So whatever your definition for good is, whether it's how fast the code runs, how small it is, how extensible it is, how quickly you can write it, like whatever your metric for good is, then if you make your code twice as debuggable, then you can make your code twice as good, right? And it completely dominates software. Completely dominates software development. And I just don't think we give it nearly enough attention as an industry, right? There's always lots of talks and presentations and tools around performance and languages and architectures and, whatever the architecture du jour is, microservices or whatever, publish and subscribe architecture. There's loads of stuff on this. And I'm not saying that's not important. It is all important stuff. But debugging is underpins all of it, right? And I think is even more expensive. And that's why I started a company called Undo, which provides debugging tools. And one of the interfaces onto our tools is GDB. So I learned a lot about GDB and learned a lot about other debugging tools in the course of running my company. And so that's kind of the knowledge that I'm here to share with you today. So we can do better than printf, right? And we've got all of these different tools available, and we can, this is how we've got this, just a few of the tools that we've got available, but we've got these different classes of tools available. Now, I think most people most of the time don't use any of this stuff, right? Most of the time they just use printf, and I think sometimes printf is the right tool for the job, but often it's not, right? It's just easiest. So let's take about these different kind of debugging tooling, different categories of debugging tooling, right? We've got the things that the obvious debugging tooling is the debugger, right? And there are different kinds of debuggers. If you're debugging C++ code on Linux, GDB, LLDB, TotalView, probably kind of the main candidates. There are others. There are lots of front ends especially onto GDB, also onto LLDB, but I'm talking about the debugger itself. I'm not, by the way, today going to talk about GDB front ends like VS Code, or Eclipse or CLion. There are lots of really good front ends to GDB and to LLDB, Xcode. I'm not going to talk about that stuff. I'm just going to talk about the underlying debugger. I could do another talk on that, and one day I will. But there are other things. There's record and replay type tools. So a thing called RR, stands for record and replay, runs on Linux. Live Recorder, also on Linux. If you're running on, this is a talk about Linux, C++. If you're running on other platforms, specifically Windows, there's a time travel debugger in WinDBG. But we're talking about Linux here. There are dynamic checkers, right? Valgrind, sanitizers. Hopefully we'll show some of those today if we get time. There's also static analysis, which I'm not going to talk about today, but I'm just going to cover here for completeness. So static checkers, are they debugging tools? Maybe, but they're more kind of, let's categorize these things a bit like what they're for, right? When would I use? It's all about using the right tool for the job. So the debugger, really what it's good about is telling you what is my program doing, right? I sometimes give I like to give sometimes the analogy of, you ever see the movie The Matrix, right? And it popularized the cinema style around that time of the bullet stops in midair and the camera pans all around and see from all different angles what's happening when time is stopped. Right. And that's really what the debugger does. It stops time and it lets you see, what is my program doing right now? Maybe I can run forward to some other point and have another look, but what is my program doing? Record and replay tools, they tell you, what did my program do? Right. So it's past tense. What happened? Which is, often what you want to know, but different things for different jobs. Dynamic checkers, really what they're good at is telling you, did an instance of a certain common thing happen? Right. So let's say we'll see this in an example, but right, a buffer overrun, very common kind of bug, particularly with C and C++, and it will just it's very good at finding instances of common bugs. I think every bug kind of falls into one of two categories. I think in this sense, it's is it one of the 50% of them are all basically the same. There's buffer overrun. There's a simple race condition with a missing lock. There's a use after free. There's memory or other resource leak. It's like a 50% fall in this kind of bucket of just like there's not that many of them, and we make the same bug again and again and again and again. And the other 50% are like all unique, right? And they're just special to you, and it's a logic error, and it's something about your program. So dynamic checkers are very good at finding those instances of the common bugs that we all make time and again. Static analysis kind of does the same thing. Looks, again, it's very good at finding those common instances. But rather than saying, did thing X happen when my program run, it's saying, could this particular thing happen, right? Could there be a memory leak here? So this kind of, I think, categorizes the different kind of tools. So we'll look mainly today at GDB because there's just loads of it, right? And as Yeet said at the beginning, I'm kind of the GDB guy because of what I do for a living in terms of running undo.io, and I like to do lots of talks on it. And it's just a great topic to do talks on because there's just loads of it. There's so much of it, and we'll just scratch the surface today. There's almost certainly more to it than you realize. By the way, almost every time I give one of these talks, I learn something new about GDB. It's kind of fractal in its like richness. We won't talk about LLDB or total view, but just because we only have an hour. Then I'll get on to hopefully we'll get time to talk about Valgrind and sanitizers a little bit, and we'll show just some examples of really how easy they are to use if you're not using them already, like you probably should. Maybe not all the time, but at least like in your CI or in certain situations. And then hopefully we'll get time to look at a record and replay, and we'll look at RR, which is an open source tool, which is good at actually GDB can also do a bit of record and replay, or as it's more commonly called these days, actually time travel debugging. You know what? In fact, I say these slides a few times. If you'll forgive me, I'm going to just edit that live. There we go. Time travel. Oh, but my anyway, that kind of doesn't quite work. Anyway, we'll move on. So yeah, I need to fix that. Move on to the next slide. So we're going to spend most of the time today on GDB. So let's get into GDB, right? So I don't know. Can we do a quick like poll, or can people? Is there a way to raise your hand or something on this StreamYard? Is there any way to interact? Because what I'd like to know is who uses GDB at least sometimes. Oh, you're muted.
Sorry. Yeah, the audience can ask their questions in the chat.
Okay. Yeah. So maybe you can put it in the chat. Yeah. Say like who. Okay, we got a bit of. So just sort of say yes or me or something if you use GDB more than once a month.
Yeah. So
GDB more than
your audience,
more than once a month.
Your ++ community in Turkey, do you use GDB? I think they are shy.
Yeah, they're very shy. Oh, there's no one there. We're talking to. Hopefully, we've got some few people. We've got at least a few on. Or maybe you don't use it. Maybe we're just starting. Yes.
Yeah,
okay,
Johnson. Yes. Yeah.
Great.
Johnson,
yeah. Okay. So that's what most people say, right? Most people say, yeah, they use it sometimes, but most people, in my experience, they'll use it like, well, only when they're really stuck, right? It's kind of an emergency tool. Because it's not a lot of fun. Oh, but someone here uses it every day. Okay, great. So, all right. Well, do chip into the chat if you have other things you want to say, or things you want to add. Like I say, my goal always with these talks is I want to learn something new every time, right? So, and I haven't yet had a talk where I haven't learned at least something. So, tell me something I don't know, or tell me something I'm getting wrong. Okay, always have multi-threaded programs. We'll come on to multi-threaded programs. We can talk a bit about that.
All right.
Some stuff, and maybe we can get into. Yeah, it's it can be tricky there. So, all right. So always what you usually see is a mix. I find in my experience, any professional C++ developer working on Linux uses GDB sometimes, and you get a big mix from like once a year, once a month, once a week, every day, and you just get a big mix of people. But so here's some stuff that I think hopefully everybody will learn something in even on this very simple essentials slide. I want to hit what I'm trying to do here is get a mix of some stuff for people who don't use it very often and some stuff for people who use it all the time. So when we run GDB, we run it like this, right? GDB a.out starts the program unless you debug a.out. You probably knew that. Everyone knew that. Then you runs the program until it gets a breakpoint. You probably knew that. You probably knew about continue, step, next, break, delete a breakpoint, and print. So print an expression. Look at this. My I just like, why is that all? You know what? It's like in different. Depends on the browser you're using. I think with Google Slides, quite what display result you get. Anyway, that'll do. So you probably knew all of this. And these are kind of I think the basic commands. Like if you know all of these, you can get some value out of GDB. But even these commands are more simple than you probably may have realized. So when I run the program, I can put some arguments, right, between the run and the after run, right? And those get set as kind of, command line arguments to my program. You probably knew that. But I can set them beforehand by set args, and then set args foo will then mean that the command line argument foo always gets passed to my program. Did you know when I type run, what usually happens from GDB by default, at least, is it will run it through a shell, through your system shell. And so things like, star and, other kind of expansion, special characters in the shell, redirection, that will all work, right? Unless you did set start up with shell off, and then GDB will start your program directly, not via bash or whatever your shell is. So that can be kind of a good thing to know happens and to know how to control, because sometimes that's kind of, you find that's what you need. When you type continue, you can add an argument to continue. You can give it a number. You can continue 3, and that will skip the next 3 hits of the breakpoint you're continuing from. If you're not continuing from a breakpoint, then it's just ignored. But if you are continuing from a breakpoint, it'll skip over the next n times that breakpoint is hit. So that's quite useful if I'm inside a loop with like 10 iterations and I keep hitting the breakpoint. I can just go continue 9, and it will skip over the remaining iterations of the loop. Or I can add an argument to step or to next, and it will step or next that many times. So if I say step 10, it will step forwards 10 lines of code, obviously stepping into functions. Next will step forwards 9, stepping over function calls. If I do a breakpoint, I can breakpoint at a line, file name and line number, or I can breakpoint at a particular address. If I know that I need to stop at an address, maybe I've got some jittered code, I don't have a file name, or maybe I can just give a function name, or in fact I can give class : function. In fact, I can give class : function, and then I can give the arguments to that function if I've got an overloaded function. If I don't have if I have an overloaded function and I don't specify which type signatures of the function I want to break at, it will just put a breakpoint on every single one, and then they get different numbers. So maybe breakpoint 3, and if there are 4 of those different, if the function is overloaded 4 times and I don't specify which one, I'll get breakpoint 4.1, 4.2, 4.3, 4.4. If I delete breakpoints, I can delete a range. So I can delete 2 - 4 to delete the range 2 to 4. Breakpoints all get numbered with this unique number. So do watch points, so do catch points. Print, there's loads of different options to print. Here's one you might not know about. -vtable will enable printing of C++ virtual function tables when I print an object. So I can actually see if I've got something, I'm debugging something that's just mad and I suspect my function tables aren't quite doing the right thing, I can get GDB to tell me about the function tables. Right. So hopefully that's just a little example of how there's more depth here than you first realize. Okay, enough on slides. Slides are, okay, but I prefer demos than slides. I think most people do. So let's show TUI mode, TUI, text user interface mode. So when I use GDB normally, so here's my terminal, and let's have a look. We've got a few programs here. Let's do hello. Actually, I'm going to go -G3 because that gives me a little bit better debug information. Actually, this program is so small it won't make a difference, but -G3 generally is a bit better than -G, although the debug info is a little bit bigger. Anyway, I run that. I run it in here. Start, by the way, is like putting a temporary breakpoint on main and then run. Just to save me a little bit of typing. So I like to do start. And here I am. So this is all like normal, right? You recognize this from GDB. Well, I'm line 6. Tells me where I am. That's kind of useful. I can type list and give me my program out. Now, this is like okay, but very, kind of 1970s type user interface, right? So if we want to be a little bit more modern and bring it screeching forward into the 1980s, we can go layout. Oh, sorry, we can do different ways of doing this, but I'm going to do it this way. 2E enable. And then that gives me this nice kind of cursive style interface. Now I can see my code at the time. And when I type next, it moves forward that line. And you can actually see, look, the output got kind of garbled here because my GDB and the program I'm running is sharing a terminal. That's okay. I can control L to get rid of that. If I want a little bit more information on 2E mode, I can go, if I go, watch this, if I go control X2, looking at the assembly.
Why did we see world only and not hello?
We saw, well, let me cycle through. Let's get there. So we saw world because I did a next over that printf, right? And that printf printed out hello world. So what we actually saw was it said hello world, and then straight away GDB printed the GDB prompt over the hello. So that I actually did that deliberately as an example of when GDB and your debuggy application, what GDB calls the inferior, when GDB and your inferior are sharing a terminal, sometimes they kind of step on each other. But it's okay. Control L will reprint the screen. If I go Control X2, I'm looking at assembly. I did Control X2 a second time. Now I'm looking at the assembly code and the source code. So oftentimes we determine there's definitely a compiler bug, right? I've ruled everything out. It's definitely a compiler. It's never a compiler bug, right? You always realize in the end it's not a compiler bug, but sometimes you're convinced it is actually, well, maybe really occasionally it is a compiler bug. Or maybe you just want to really understand what the hell is happening, and you can look at the disassembly and the source code at the same time. But if I step I, that will step a single instruction. And so I can just step through and see exactly what it's doing. If I step off this, it's going to return out of main. The main is not actually the end. It's neither the beginning nor the end of my program. There's like all this library code that runs before main starts and after main finishes. And we can, anyway, step through all of that. I can finish out of that function. Well, no, I can't because it's not a regular function. Anyway, so that's let's actually restart the program. One of the things I often hear people get frustrated with 2E mode once they first discover it, super useful. I mean, okay, you could use VS Code and stuff, and that works great. But you've got to have it all set up, and maybe you don't have VS Code available. Maybe I've just SSH'd onto a machine somewhere. I have GDB, but I don't have VS Code. This is just a useful base level kind of way of driving GDB. It's the way I drive it by default, definitely. Well, one of the things that's a bit annoying is when I press up arrow, right? So when I'm running GDB, if I often use up arrow and down arrow to go to the previously entered command. I don't want to type all that stuff every time, right? If I'm printing out a long expression or something. And if I up arrow in 2E mode, look what happens. I'm scrolling, and down arrow, I'm scrolling up and down in this disassembly window, right? Which is not what I wanted to happen. If I'm in the default 2E mode, which I go like this, I'll get back there. Hang on a second. I can also look at register values, by the way, but let's go back to the default 2E mode. Up arrow and down arrow does this, right? Left arrow and right arrow, even less helpful, they do that. But there's a couple of ways around this. So if I go Control P, then I get my history, and Control N. So P for previous, N for next. Control A to go back to the end of the word, Control E to go to the end, sorry, correct to the start, or Control B to go back a character, F to go forward. So I don't need my arrow keys. I can use Control keys, and then that's the kind of standard GNU Emacs type bindings. Or if I don't want to remember all that, I can go Focus, Command. Actually, another trip with GDB is use tab complete to kind of discover stuff. So actually, I should have said at the beginning. So GDB is I mean, I think GDB is a great piece of technology, really helpful, so rich, so powerful. It is not a friendly user interface, and it is particularly actually the UI is not too bad once you get used to it. So probably a lot better than say Git, but it's not discoverable, right? It's definitely not discoverable. But tab complete kind of helps a bit. So I can go focus. If I tab, I get the possible completions of that. So these are the window names, right? So I can focus on the command window, or I can focus on the source window. I never quite worked out what focusing on status does, but apparently that's a thing you can do. Next and prev, I guess, pretty obvious for the next and the previous window. So if I focus on the command window, now when I do up arrow and down arrow and left and right, I get those are going to the those are being typed into the command window. So it's slightly weird when I type characters that if I put the focus back on the source window, if I type most characters like A, B, C, the source window can't handle them, so they get sent to the command window. But other arrows like up, arrow, and down, keys like up, arrow, and down, then it can do that. Okay, so that is PUI mode in a really quick version. There are actually different ways to enter TUI mode, by the way. So TUI enable is quite a relatively new thing. You can also go layout, and there's different layouts. Tab, again, to see the different ones. But layout source is basically the same as TUI enable. And the other way you can do it, by the way, is Control XA, and that will toggle. Control XA toggles between the two. There are different ways to go in and out of TUI mode. TUI enable, disable is probably the most obvious. And then Control X2 in particular cycles through these different window views, including my registers, which can be quite useful. Right, that's it for TUI mode. I've got a few questions here. Let me just see what we got in the chat. So GDB monitoring is not easy. Yeah, we're trying to talk about that. Debugging embedded systems usually involve a sad developer and a non-blinking LED. Yeah, well, maybe if you're really, really early on with your non-blinking LED, but like you can, in all but the very most embedded systems, you can get a GDB server running on that embedded system, and you can remote debug onto that GDB server. And the minimal GDB server that you need to write, by the way, is quite small. It doesn't need to be anything like complete. It just needs to respond to a handful of commands. You won't have the full GDB functionality, but you can get that going. Another program here. Can a program detect that is running with a debugger with GDB? Is there a library in C++ where we can understand this situation? So there are some tricks you can do. And one, it's not like perfect, but it will kind of mostly work, is that GDB works using a system call, a set of system calls you call ptrace, right? And you can try to ptrace yourself. So if you go like this, let's see if we can, if I go ptrace, trace me, you have to ignore these other arguments. They're not really going to be interesting here. Int r equals, and if r fails, then printf I am being debugged. That will mostly work. So hash includes sys ptrace. So ptrace is the kernel mechanism that GDB uses to control the program that it is debugging. But there's a restriction in Linux when a program can be traced by only one tracer. So let's see if this works. This is a dangerous thing to do, obviously, because I've never tried this before, but I think this will work. So if I run this normally, hello world, if I run it in GDB, there we go, look at that, it worked. I sometimes say at the start of this talk, by the way, how many lines of code do you think you can write and have it work first time? And like the answer, I think, is usually a lot less than 10. And you know, as a point of how important debugging is. And then I ask, how many lines of code do you think you can change and have it work first time? And I think on average, I mean, you might be a better programmer than I am, but for me, on average, that's like less than 1 lines of code that I can change in an existing project and have it work first time. And it actually worked first time. That's pretty cool. But like, it's always a surprise. Anyway, yeah, that's a way you can tell whether your program is being debugged. It's not perfect because there are other things that use ptrace, such as strace. So it's going to go. Let's do it. So if I go like that, then it's being debugged because strace is tracing it. But well, maybe it's being debugged because it's being debugged with strace. Yeah. Really want to get funky, you can look inside proc self status has a thing called tracer PID. If that is a non-zero number, then that's a process ID, and you can look at that process ID and you can determine whether it's GDB, and then you can know whether it really is GDB if you really want to care about that. All right, next question. Remember some video games detecting the presence of winged debug as an anti-piracy measure? Yeah, exactly. So you can do that, right? That's a legit thing to do. Am I being traced? If so, like, refuse to run or something. Obviously, it's kind of less of an issue generally in the Linux world, but yeah, okay, right, all right. In the chat, what's this? You've been looking at it for a long time now. So what is this? Anyone know what this is? All right, I'll tell you. It's Breakpoint. That's what it is. This is Breakpoint, not Point Break, which is a terrible film. Do not watch the film already. Yeah. Breakpoints, right? Yeah. So just as I said earlier on, there's more to breakpoints than like you might realize. So break foo, you've probably seen that. That breaks on a function foo. Tea break, I quite like. Tea break sort of sounds like tea break, right? It's like taking a tea break. It's something that English people do a lot. Yeah, it's a temporary breakpoint. So as soon as the breakpoint's hit, it gets removed. So let's show that. Actually, I'm going to just copy something. I forgot to copy over, I think. So I've got a program here. Bar. It's very simple, right? It's just like calls this function bar a bunch of times. Doesn't even have a function called foo. I don't know why I called it foo bar. Anyway, let's compile that. So start the program. Let's go into 2 mode because I just think 2 mode is nicer. So I can put a temporary breakpoint on bar like that. Okay. And now I can continue my program. It hits that temporary breakpoint. Okay. But now the breakpoint is gone. And I can see what breakpoints are available by the info break. So it's gone. And I continue. It's going to run to the end. So, and actually when I run like start, that just basically puts a temporary break to T break on main and then run. So it does that and hits the breakpoint main, info break. Breakpoint doesn't exist anymore. Notice though that this number is being incremented each time, right? So this is temporary breakpoint number 3. If I put another tape, because I'm in the same debug session, so if I do another T break, I can do TB by the way, as an abbreviation, and that's number 4. And then if I put breakpoint on, I can run that. So it's gone. Put another breakpoint, a regular breakpoint on bar. That's breakpoint number 5. So every breakpoint gets its own number, whether it's a temporary breakpoint or regular breakpoint, or in fact a watch point or anything else. Our break is kind of cool, right? So our break stops on a regular expression match. So basically, breaks on a regular expression match. So it's gonna, if I know like I've got a library and all of my functions start with a common prefix, I can put a breakpoint on all of those libraries functions. So let's do like, so for example, I can go R break. Now I have to, it's a, what's the phrase? Like a permissive match. But so if I R break hat str, that's going to put a breakpoint on every single function that starts with the characters str. And then I'll just continue because it's paginated. So there we are. So it's set 29 or minus the 5 that I already had on, and all of the functions start str. So that can be quite useful sometimes. I can have thread specific breakpoints. So I only want my breakpoint to stop on a certain thread, thread number 3, for example. I can do that, right? I can have conditional breakpoints, right? They only stop when a certain condition is non-zero. And I can, a nice thing by the way is also I quite like, so delete, you probably know, disable is quite good. So often I've been debugging something for ages and I've got a whole set of breakpoints set, and now I want to set a breakpoint that kind of, it has priority over all the others. I don't want to delete them all because like I probably want them back again, but I just temporarily want to have only one breakpoint matter. So I can just disable all of my breakpoints, put my breakpoint that I care about, run to that breakpoint, and then enable all the other breakpoints back again. Quite a useful trick. There was a question earlier. I'm going to jump around a bit. There's a question earlier on multi-threaded debugging. Oh God, not the regular. Yes, right. Not exactly regular expressions. They're always a pain. As far as I know, no one has yet produced a debugger for regular expressions, but there's definitely a gap in the market on that one. Right. Let's look up. Let's quickly go for threads. I don't think I've got slides on multi-threaded debugging here. I'm never going to get through all of these, but I like to have stuff that I can jump around on. But yeah, I did. Look, okay, all right. So here we go. So I have way more slides than I can show, but I can jump around. So threads in GDB. Can I just ask? So you said you had someone has said whoever was said they have problems with debugging threads. Could you just post in the chat exactly what the a sentence or two on the kind of problems that you had? Oh, Yeet, you're muted again.
Sorry, yeah. Islam and Genji Nihan, can you provide more details about why debugging multi-threaded programs is not easy? I mean,
okay, I can just give a quick overview on thread debugging. You can post in the chat while I talk. I'll answer very quickly. Have I ever used the GUD package in Emacs? No, not really an Emacs guy. Sorry, more of a Vi guy. But I'm very open-minded, and I do have very good friends who use Emacs, and I do still talk to them, and they do, and they use the GUD thing a lot, and I believe it's works very well, I believe, but I don't have really any experience with it. They're not running as we expect. That's interesting to hear. So I have heard that before, but I've never actually seen it. So you're finding that when you got a multi-threaded program, I run it in GDB and it like changes the behavior of the program. Is that what you're seeing? Because that I would not like. That's kind of surprising. Okay, I think maybe I can take a guess at what's going on here. So, if you have things like conditional breakpoints set, then what will happen is, like, due to kind of the internal way that ptrace actually works, is GDB has to continue each thread at a time. So let's say my program has 100 threads, and I've got something like a conditional breakpoint. One of my threads hits that conditional breakpoint. Then GDB will stop all of the threads, all the other 99 threads, and then it will return to the prompt. And then it will evaluate, well, sorry, it won't return to the prompt. Then it will evaluate that condition. If the condition is not true, then it will have to continue all of those other 100 threads. And so you get a lot of context switching back and forth, GDB and the program being debugged. And GDB also has some internal breakpoints, particularly on the loader. So if you're loading dynamic shared libraries, then when that happens, GDB gets its internal breakpoint happen, and again, it will stop all the threads and continue again. So things like loading shared libraries can cause like this context switching from the application to GDB and then back again. But if your program, I'm kind of surprised to hear that. If your program is not, if you don't have any conditional breakpoints and you're not hitting breakpoints at all, including internal GDB breakpoints, which basically means you're not loading and unloading shared libraries like as you're running, I'm surprised that you see a difference in threading. I would expect the OS to do like exactly the same thing. That's unless somehow GDB is doing something about the ordering of where the threads start. Oh yeah, also if the threads are being created and destroyed very quickly, If you've got threads coming alive and then disappearing, that also might cause GDB. But even so, the only thing I would expect to happen is GDB is causing an ordering of scheduling to happen that you don't usually see. And that seg fault that you see, like, I mean, it's always hard to know from these sort of descriptions, but my guess would be if you're seeing a seg fault in your multi-threaded program only when that program is running in GDB, well, one of two things is possible, right? Either it's a bug in GDB, or it's a bug in your program that you don't usually see, right? And I'm a bit biased, but my money's on the bug being in your program, not in GDB. I think that's telling you something. It's an expression. I like the expression. Sometimes I've heard you might have heard this of, "Do you smell smoke?" Right? If you're in your home and you smell smoke, you can close the door of the room you're in and pretend it's not there. That's probably not a good idea, right? You probably want to go and find what is the source of that smoke before your house burns down. So same when you're programming, when you're looking at weird effects like this. I mean, if you're running on a really weird embedded system or something, then it's more likely that it could be a bug in that implementation of GDB or that RTOS or something. But if you're running on regular Linux with regular GDB and your program segvs when you run it in GDB, only when you run it in GDB, I reckon that's a strong smell of smoke, and there's probably something wrong with your program that you just aren't seeing unless you run it in GDB. But one of your users, your customers, sooner or later will see that segv, right? So I think that'd be my first guess. I would really want to know what is going wrong
there. Greg, I actually about this matter. I had a question for the end of the talk, but yeah, I think since many people are asking about multi-threading debugging, compilers tend to optimize code in very unexpected ways. So actually, the way we write our code is not necessarily the way they're executed actually in the hardware. So the compiler can reorder the code. Whenever we put in some print statements, it enforces a sequence point. And the bug actually disappears when you put that print statement. So we can no longer find the bug. We can no longer replicate the bug and investigate further. I have never seen similar things when I'm using GDB, but is it the case? Can we see similar situations when using GDB also?
I mean, it's a really good point, and it's a real plus point for GDB and a minus for printf debugging, because when you're debugging with GDB, what you will see is what the program really does. Right now, okay, you might see a difference in scheduling of when different threads run, but there's no guarantees about what scheduling you'll see from the OS anyway, right? If you run your program enough times, you'll get every possible combination of scheduling. So I would argue that the scheduling differences are just, all you're changing is the probabilities of one scheduling order versus another scheduling order. You will see, the compiler is absolutely, and it will do this at high optimization levels. The compiler is completely free to generate the code in a different order to the order in which you wrote it, right? Even actually, if there are sequence points, if there are no dependencies between, if you've got one computation on one line and a semicolon, which is a sequence point, and another computation on another line, right? The compiler is free to order the first computation to happen after the second computation if there are no dependencies between them, right? And it will. And the compiler will totally do that in order to optimize, use of registers and, basically generate faster code. And so you'll see this when you're stepping through optimized code. People sometimes see this effect, and it can be very confusing when you first see it. I've got, a block of 10 lines of code, and I go next, next, next. And then the next, it jumps forwards, and then I do another next, and it goes back again. And that's totally legit. And it's kind of confusing as hell, because my mental model of the program for my source code differs from what actually is happening, right?
Yes.
But you know, when I'm debugging, I probably want to know that, right? It may be relevant that the code executed in a sequence different than I expected, particularly if I've got like multiple threads and, you know, they're sharing memory and like the sequencing matters in that way. Yeah, like it's well, it's probably a bad example because it wouldn't do that difference in ordering if there were globals being referenced by different pieces. So bad example. But the point is, it's like it's what you're debugging is what actually happens when the program runs for real. And so you know, yeah, it can be more confusing, but it can also be more. It can be really. It's actually, I think it's even more confusing when you kind of you like when you're debugging these gnarly issues, particularly in languages like C and C++. When your mental model of how the language behaves is subtly different from the code that the compiler generates in like a meaningful way, then that's a horrible situation, and you really want to know. And the debugger is telling you something. So yeah, you know, I think the debugger is good in that scenario. Let me just show a little bit. Okay, we've got something on core dumps, and time is just like always goes so quickly. A little bit on core dumps, a little bit on threads, and then I want to show you something that I think is particularly cool in GDB. So let me just do. So here's some thread stuff that's like maybe you'll find useful. Do we have this? Yeah, that's not the one I wanted. Hang on a second. GDB training thread stops. I made some changes. So here's a threaded program. Doesn't really matter. What it does just creates a bunch of threads and they print some stuff out. So GCC threads.c minus LP thread out. It does this. Okay, and they're all kind of running in lockstep. And so I can run them inside GDB. It does the same, right? And so my program creates 4 threads, and there's the main thread as well. So this is 5 threads. Here they all are. Now when I type continue, well, in fact, even when I type next, what GDB is going to do is it's going to start all of the threads until until the thread that I'm currently in gets to the next. So I have this notion of what thread I'm currently in. You can see this from the star up here, right? So I'm thread 1. I can look at thread 5 if I want, backtrace. Now when I next, boot mode is better, but I'm in the, let's finish out of there so we get in the C library here. Look, so I'm going to finish out, keep finishing. Here we go. When I next, it's always in that thread, same thread. My next stays within the same thread, but every time I run it, every time I type next, it's going to run all the other threads in the background. So if you're seeing that by the way, if you're seeing scheduler changes when you're typing next, that you might actually force kind of, you might force very unlikely but still possible scheduling orders to happen, right? So when I'm next or step, it actually runs all of the threads. Unless I do this, and if I set scheduler locking off. Now, when I type next, you can't see this, but it's not running any of the other threads. It's only running that one thread. But if I set scheduler locking on, so off is the default. Sorry. So let me set. So if I go set scheduler locking on, so I'm currently in. Okay, let's get that back. So I'm currently in thread 5. And the other threads I can see, they're all stuck in nano sleep. Okay, apart from this one, which is in pthread join. So if I go set scheduler locking on and I continue, so only that thread 5 is now running. The other threads aren't running, right? That's quite cool, isn't it? But except, let me show you, this is often a problem because you have to prove I'm a Vim person. Here we are. And so they've got this sleep, right? So I'm going to take that sleep out and I'm going to recompile that. And I'm going to run it, and you'll see it's a little bit different. They've got run around really fast, and they're not in lockstep anymore. Okay, that's not a surprise, right? and I'm going to run this. Okay, same thing happens. So let's see where we are. So we are one more going to be thread 1 to start with. I've just told it to use a different thread. So let's go back to thread 5. And let's set scheduler locking on. Now, all I've done is remove that sleep, right? So it should be exactly the same. Continue. Nothing happens. Nothing happens because thread 5 is in some futex internal. This is in some futex internal. This is in libc's write system call, which is probably coming from that printf. If I go thread, but in fact, I can show thread apply 3 backtrace. That'll give me just the backtrace from thread number 3. And yeah, probably it's actually in that's the way it is in the printf. Don't worry about the details. And that takes a lock inside libc, right? So thread 3 has the lock, and so none of the other threads can make any progress unless if I go thread 3 now. Set scheduled locking is still on, so I continue that. Now it'll run thread 3, which is the second worker thread. Okay, so set scheduled locking is pretty cool. By the thread apply all backtrace is a nice thing. In fact, we really want to get verbose, you can go backtrace full, and that will give me the full backtrace with all of the local variables of all of the threads. Let's just do a normal one. And if you're really lazy, you don't want to do a lot of typing, you can thread apply all backtrace, and that does exactly the same. I can't remember what thread apply all s does. Thread apply, I can't remember, but I'm running out of time, so I'm going to try and go quicker. So that's a little bit on threads. So a little bit on core files. Yeah, core files are super useful. Core file debugging, got some stuff on that back up here. Catch points are cool, by the way. Do look up catch points. So the documentation for GDB is actually quite helpful if you know what to look for, right? The man page is pretty well written, pretty complete, but it's very, like I said before, very undiscoverable. But go and look at the man, so info GDB or inline help. So I can go GDB help catch, tells me about catch points, what I can catch, what I can useful documentation, or I can go info GB catch points, and then it'll tell me all about. So the online documentation, or you can just Google it and look at the online documentation on the web. Right. Okay. Racing through. Sorry for going so fast, but time just runs away. So core dumps are, yeah, now there's certain things you can't do. You can't call functions in the inferior, for example, but most of the stuff you can do. Pretty printers, for example, Python pretty printers, which are super useful. They work in core files. And the core file is a snapshot of the program state at the end, like usually at the end when the program crashed. I can actually take a core file from a running program if I want with a command called gcore, which is actually kind of like, it's actually a script that runs GDB in a certain way. So look at this. If I run, let's run my threaded program. So I didn't want that one, I wanted that one. And let's go to another window here. So pid of a.out. So I can go gcore -p. I think I have to say -p, can't quite remember. Anyway, it's that pid. No, don't give it a p. Don't give it a p, just give it a pid. And it's created a core file. That program's still running, look, but it's created a core file of it. Okay, it's a warning, but that's not important. And so what did it call it? It called it that. And now I can load that up. So the core file might not be crash. I can take a core file of a running program. But usually a core file is from a crash. But its point is a snapshot of the program at that state. But I can do all the normal things. I can look at threads. I can do everything basically that I've seen, apart from like setting breakpoints, and continuing doesn't make sense because it's a core file. It's a static thing. What you get in a core file depends on how you've set up. So proc pid core dump filter controls what types of memory get put into a core file. Memory mapped IO generally never does. Most of the memory does by default, but you can turn things on or off with this kind of bit mask. And the rules for what triggers a core file are pretty like hard coded into the kernel, basically. Some signals cause core files and others don't, and that's just the way it is. And you can look in man7 signal to see what that is. So man7 signal somewhere has that list. There we go. Here's all the signals on what they do by default if they're not caught. And so sigabort and zigzagv, etc. will do this action core. Right, that's core files. I want to take just 5 more minutes to show you something about time travel debugging, something close to my heart, something that my own company undo.io kind of specializes in. GDB has inbuilt some time travel debugging. It's a bit limited, but and very slow. You might want to look at RR as well as an open source alternative, which works really well. Or of course, you might want to look at undo stuff, which is like super awesome. But it's kind of all the same concept. They're just very different implementations. Let me show you the built-in GDB stuff, because that's just the quickest to show. So I have a program here, sort, which doesn't do anything. It basically, here's the source. Oops. Just like gets a bunch of random numbers and does a bubble sort on them, right? And then exits. But I happen to know that there is a bug here. I'm just going to run that in a loop. I'm going to run a bunch of times. And eventually it's going to fail. It will fail, trust me. There we go. And it's made a core dump. So here's the core dump it's just made. So if I go, I think that's the one. Oh God, I think that's not done what I wanted, because I got this. It's put the core dump somewhere else. Okay, so one of the things about core dumps is it will dump it in this place, this proxys kernel core pattern. And I think I've got, this is a new installation. It's got this apport stuff. And so what that does in the core pattern, it starts with a pipe character, which will then pipe the core file into some other defined program, whatever's after the pipe. And in default installations of Ubuntu, because it wants to do your program's crashed, do you want to send a result? So I'm going to do that again. And now we just have to wait. I've got 3 minutes. Let's hope it crashes quickly, because we're going to lose valuable time. This is the trouble. This is an intermittent, spurious bug. It's actually, yeah, based on what time returns. So it's like, there we go. Right. So hopefully now that exists. Yeah, there it is. Right. So GDB, what was I running? Sort core 23575. So this is the core file at the time that program terminated, and it doesn't look very useful. If I get a backtrace, looks like some kind of stack problem, right? Very, very unhelpful. Sometimes that's the way with core files. The information I've got this snapshot at the end of time. The information that I need is gone, right? So what I really want here is time travel debugging. So I'm going to run this. I'm going to put a permanent breakpoint at main, and I'm going to attach some commands to it. Commands is a cool command. Commands lets you attach commands that will happen automatically every time a breakpoint is hit. And so in this case, I'm going to do record, which turns on the inbuilt recording, and end. I'm going to put another breakpoint at exit, and I'm going to attach some commands to that. Well, one command actually to rerun it. And I'm going to set pagination off, and I'm going to set confirm off, and I'm going to run it. So what this is doing is every time it gets to the breakpoint main, it issues that record. Wow, that was quick. We got lucky. Cool. Right, it's going to issue that record command, and then it runs the whole program with recording. If it gets to exit, it just reruns it. But it didn't get to exit. It hit that segv. It looks just like when I looked at it in the core file. It's all just garbage. But if I reverse step I, it's going to go backwards one instruction in time. And now when I backtrace, look at this, we're in kind of sensible land. Let's go into tree mode. So it looks like some kind of stack smash. In fact, I want to look at the this assembly code here as well. So we are, that's that breakpoint. Here we are. We're at a ret instruction. Ret on x86 is a fully descending stack, so it will jump to whatever is at the top of the stack pointer. So if I print the stack pointer, I can do it like that. Okay, that's my stack. That's the top of the stack. So it's going to go to whatever is in that. So if I look at long star $XP, that's the return address, and that doesn't look like a valid. X is a short for examine, by the way, so I can look at that. Yeah, that's an invalid address. It's returning into hyperspace. No wonder it's sig faulted. So my stack contains garbage. I need to know, like, at what point did garbage get run into my stack? Well, I can use a watch point. Watch point is kind of just like what Microsoft calls a data breakpoint. Rather than run until a line of code has changed, I'm going to run until some data is changed. I'm going to make that a location watch point. Don't worry about the details of that. And I'm also going to do something because GDB's inbuilt time travel debugging has a bug. So I'm going to say actually set can use hardware watchpoints, and I'm going to do that instead. And now so I've set a breakpoint at the top of the stack, and now when I reverse continue, I'm going to go back to when that location in memory changed, right, to when that top of the stack changed. And so here we are. So I've gone back in time until this line of code, which is like, that starts to look quite suspicious. So print I is 35. If I go up a bit more, I don't want this assembly code now. Let's get back to this. So I is 35, and it's looking this array, and I can say, what is array? Well, array is only 32 elements long, and here's my bug because it says % size of array, and that's a size in bytes, and actually it should say % size of array, number of elements. So sorry for racing through that really quickly, but I wanted to show you a bunch of cool stuff, and particularly time travel debugging, which so the biggest problem with debuggers is they tell you what is happening, and often what you want to know is what happened. Time travel gives you that ability to go backwards. GDB can do it inbuilt, although it is mighty slow and a little bit finicky, as you saw with the way I set it up there. And there's a thing called RR, record and replay, which works much faster. Also can be a little bit finicky, but does work very well where it works. Doesn't tend to work in like AWS and places like that, but if you've got a local machine you can run it on, tends to work really well. And there's our own stuff at undo.io, which I strongly encourage you to check out. Right, sorry for going over, everybody. We're just a few minutes over, but there's a lot of stuff that I wanted to say. And thank you for the good questions and thank you for listening.
It's perfectly fine. I mean, if you have more things to add, feel free to do it.
Yeah, I mean, I think we should probably wrap it there. I could literally go all day, right? And I do have like enough content to go for a full day. And we go into companies and do training on GDB and other stuff. So I'm very happy to come back another time and do a follow-on session. Let me just look at some of the questions here. Ulimit -C unlimited. Yeah, that was so in the chat there, ulimit -C unlimited. Yeah, that's often a thing with core files. Yeah, the other thing is this a port thing, which kind of I think gets in the way. Yeah, good, and some nice comments. Yeah, we could listen all day. Well, look, let's I have to go. Unfortunately, I've got other stuff I need to do. But let's schedule another one, and we'll do like next bits. I have. Oh, I should say, if you go to undo.io, there's a thing called Watchpoint. There's a page called, if you can Google it, well, I can just show you, right? Mm-hmm. And there's loads and loads of stuff. If you go undo.io, this is on here is somewhere. Hang on, the Watchpoint, and that has a whole bunch of tutorials, they cover a lot of what we just covered, but a lot of other stuff as well. There's my dog. That's my dog, Bear, by the way. He isn't very good at programming, but he keeps me company. So yeah, do go have a look at undo.io resources, GDB Watchpoint. It's got a whole bunch of tutorials, both videos and written tutorials as well.
Yeah.
Cool.
Thank you very much, Greg. I think this concludes our insightful talk on GDB and debugging in general. I think this was very brilliant. I mean, our community members, I hope you found this session as informative as and enriching as I did. So yeah, uh, I think it was very good. I myself, I never knew about the TUI, for example. I think, yeah, it was very good that Greg demonstrated its strengths to us, and also, yeah, he demonstrated a lot of um, GDB functionalities that probably most of us never knew before. So yeah, thank you very much, Greg. It was a very nice talk.
Thank you. Thank you very much. And yeah, thanks for the opportunity. Thanks for the great questions. Great interaction, actually. Really good engagement. Loved all the questions in the chat. Yeah, maybe we can do it again another time.
Sure.
Thank you, everybody.
Yeah. So hopefully see you later. Bye.
Bye-bye. Bye.